In this video we're going to be talking about inverse functions, and then we'll also be pulling in some of the ideas from composition functions that we talked about in the last section and how that concept is related to inverse functions. So first of all, let's start off with the definition. The inverse of a function or a relation, I guess I should pause a second. We need to refresh our memory, I should say, on the difference between a relation and a function. And this is something we talked about way back at the beginning of the year. So a relation is simply some pairing between x and y values, and functions are special types of relations where each x value is paired to only one y value. So remember, not all functions are relations. So then we can talk about the inverse of a relation or the inverse of a function. And whether we're talking about a relation or a function, the definition is the same. The inverse is simply what you get when you switch the values in the domain and the range, meaning you simply switch the x values with the y values. So let's say we have this relation down that I gave you at the bottom of the slide, where we've got these x values 0, 1, 2, and 3, and those x values correspond to these y values of -1, 0, 2, and -6. To find the inverse of that relation, all you have to do is switch the x values with the y values. So that means your new x values become -1, 0, 2, and -6, and your y values become 0, 1, 2, and 3. It's that simple. The inverse of a relation or a function simply switches the x values with the y values. Now there is some notation that you need to be familiar with, and this notation is related to function notation. So let's say f of x is our original function. Then the notation that we're going to use to represent our inverse function looks like this, and we read this as the inverse of f, or f inverse. You do need to be cautious. It looks like this -1 is supposed to be an exponent. It is a superscript, but it doesn't mean that we're necessarily raising our function to the -1 power. It means that we are taking the inverse of our original function, and again, based on that definition we just talked about, that simply means that we are switching our x values with our y values. So let's do a couple of examples. First, let's see how we can find the equation of an inverse. So here I've given you the equation y equals x squared plus 3. If we want to find the equation of the inverse, then we need to go back to the definition of an inverse, and that is simply that we're going to switch our x values with our y values. So in our equation, that means that everywhere we see a y, we're instead going to write an x, and everywhere we see an x, we're instead going to write a y. But of course, we typically don't write our equations, or we don't typically have them solved for x. We would prefer to have this solved for y. So we're just going to take the algebraic steps necessary to solve this equation for y. So first I'm going to subtract 3 from both sides, so I'll get x minus 3 equals y squared. And then to isolate y, I need to take the square root of both sides. And of course, whenever you take a square root, you need to take the positive and the negative root. So this becomes y equals the positive and negative square root of x minus 3. So this equation here is the equation for our inverse function. Now if we wanted to write this out using function notation instead, that would mean we would have represented our original function with f of x equals x squared plus 3, and our inverse function, we would have used that notation that I introduced on the last slide, so we'd have f inverse of x equals the positive and negative square root of x minus 3. Now let's say that we want to graph a function and its inverse. And I'm going to go ahead and use the functions that we just worked with on the last slide. So our original function was f of x equals x squared plus 3. Hopefully you remember, we've talked about this back in the first semester. If it's x squared plus 3, that is just a translation of our parent function x squared up 3 units. Let's see if I can sketch this decently. There we go. So we have taken our parent function, our parabola, and we have just shifted it up the y-axis 3 units. So there is our function f of x. Now on the same axis, I want to graph our inverse function, f inverse, and remember that's the positive and negative square root of x minus 3. So that means we've taken the parent function, the square root of x, and we have shifted it to the right 3 units. And so that's going to look a bit like this. Now, of course, this is just a rough sketch on my part, so you're going to have to use your imagination slightly here. But if this is our function and its inverse, you might be able to see that there's a relationship between the graphs of the function and its inverse. And that relationship is always going to hold true for any function that you graph if you're graphing the function and its inverse on the same axis. And that relationship is that the two graphs are simply reflections of each other over this line that I've just sketched in, and the equation for that line is y equals x. And hopefully it makes a bit of sense why these two graphs would be reflections of each other over this particular line, y equals x. And that's because, by definition, a function and its inverse are related to each other simply by switching the x and the y values. So again, this relationship between a function and its inverse, that always holds. They are always reflections of each other over this line, y equals x. If you recall, back when we first started talking about functions, we talked about a few different ways to figure out whether a relation was actually a function. Because remember, a function can only take each x and pair it with one y. If you recall, we also talked about looking at the graphs of relations and determining whether that graph represented a function. And the way we were able to test that was to use the vertical line test, otherwise known as the VLT. So in that, we would pass a vertical line. I'm going to try to pass my, there we go. So here's my vertical purple line, and I'm going to pass, if it'll let me, here we go. I'm going to take my vertical line, I'm going to pass it over our function f of x. And because our function never hits our vertical line in more than one spot, it truly is a function. So we've confirmed that f of x is a function using the vertical line test. However, if we then pass our vertical line over our inverse relation, f inverse, notice that this relation starts to hit our vertical line in two spots immediately. So that means that our inverse relation is not actually a function. F of x is a function, but f inverse of x is not a function in this case. So it doesn't pass the VLT. Another test that you can use to determine whether or not the inverse of a function, the inverse of a function is a function itself, is to use not the vertical line test, but the horizontal line test. So we'll abbreviate that, the HLT. And I'll try to create a horizontal line here. There we go. And to use the horizontal line test, you use it the same way that the vertical line test works. Let's see if this, nope, sorry about that. Let's try this again. User error. Here we go. I think it'll let me use this vertical line. Oops. Having some technical difficulties, bear with me. There we go. Okay, so here's my purple vertical line, and what I'm going to do is I'm going to pass that over my original function f of x. And if I pass this, I'm sorry, I just said vertical. If I pass this horizontal line over my original function, and the horizontal line intersects my function in more than one spot, which you can see that it does, it's going to hit my function in two places, and almost everywhere on the function, then that means the inverse of this function will not also be a function. So again, to test to see whether the inverse of a function is itself a function, you can either use the vertical line test on the inverse, on the graph of the inverse, or you can use the horizontal line test on the original function. So I've got a few more examples to do with you all. So let's say we have some new function g of x, and it equals 6 minus 4x. First of all, let's talk about what the domain and the range of g would be. A couple ways you could figure this out. You could go ahead, you could just kind of think about what that graph would look like, or if you need to see the graph itself, you could draw it. Let's just see if we can figure out what this function is going to look like. Hopefully you notice that we just have x to the first power here, and x only shows up once, so this means we have a linear function. If you needed to, you could rewrite it as negative 4x plus 6. So this means we just have a line in slope-intercept form. It has a negative slope and a positive y-intercept. So its graph would look something like that. So we can talk about the domain and the range. Domain again goes with all of the x values. In this case, our domain, of course, will be all real numbers because there's no value of x that we couldn't plug in. And the range, if you look, you can sort of see if you go up and down the y-axis, there is no value of y that we wouldn't end up having, so the range is also all real numbers. Now the second part of this question asks us to find the inverse of g, which of course we're going to call g inverse. The easiest way to do that is to simply start with your original function, which is y equals 6 minus 4x. And then like we did earlier, you're going to switch the position of x and y. So it becomes x equals 6 minus 4y. And now we are going to solve this new equation for y. So we'll subtract 6 from both sides, and then divide both sides by negative 4. So we're going to get y equals negative 1/4 x minus 6. And if you wanted to put that in slope-intercept form, you just need to distribute the negative 1/4. So it's negative 1/4. Might not be able to write that small. There we go. Negative 1/4 x plus 6/4, which is 3/2. Okay, so using this same function and its inverse, let's talk about what the domain and the range of g inverse are. So we just said that g inverse is negative 1/4 x plus 3/2. So again, we've got a line here,